Okay, I think we'll get started. So today we're going to talk about one of two group theory aspects we're going to employ with the Blaschke products. This I'm referring to as the Blaschke group, and what we're looking at here is the effect of the Blaschke product on the unit circle. So we know the Blaschke product of course maps the interior of the disk to the interior disk, but also maps the boundary of the disk or the unit circle to the unit circle. Now what we're going to do is we're going to consider one point, can be any point on the unit circle, as a target point. That is the point in which the Blaschke product will map to. So associated with that will be the pre-image of that point, so the set of all the points for which the Blaschke product maps to that point. Now, without loss of generality, we can choose one particular target point, and usually that is 1. So we'll choose this as 1. If this were a normalized Blaschke product, then we know that B of 1 would map to 1, but we don't even need to be worrying about that. We just know that that our target is 1. And then due to the nature of the Blaschke product, if we have an nth degree Blaschke product, then we anticipate n solutions to this problem. So n image points, pre-image points. So that is, if we look at the inverse image of B1, we should get a set with n points in it. Now each one of these are on the unit disk, so they can be of the form like this. So they have a certain amplitude of 1 and then phase, and we can order these such that they're ordered around the disk in a counterclockwise manner, such that the phases for 1 is less than 2, is less than 3, and so on. Notice when we get all the way around, then we just repeat. So we're going to be mod 2 pi. So the kth one of these, if we go above n, will be just this mod 2 pi. And so what that means is that k equals L mod n. So we just have L of these, and then they repeat these little segments. Now, what's interesting to note is that so if we take a point here and move around the unit circle, so if this is just some point, some variable on this pre-image space, and we move around the circle, then the Blaschke product will map that to the disk precisely n times if it's an nth degree Blaschke product. So it's an n to 1 mapping of the unit circle. Now, what's particularly interesting, though, is that if we start inside one of these intervals, and we start at one end and go to the other end in a counterclockwise manner, then we map to the unit circle once. And then if we were to step to the next segment, we map again and again and again, and as we get all the way around, that completes our n to 1 mapping of the unit circle. So, to be a little more precise, B will map one of these intervals to the unit disk in a 1-to-1 and onto manner. Okay, so what we do here is just this is a little bit formal, so we'll just kind of talk through it quickly. We can imagine a set of functions that are restricted in their domain, such that they're restricted to one of these intervals. And then the range of this will be the disk. So we're going to imagine that we've got this function that will map this to this, such that they're equal to the Blaschke product in that interval. So for any variable within that interval, these functions match up. So then we can think of, well, two things. We can, this allows this to be a bijection, which is helpful. And then we can build the Blaschke product sort of as putting together these segments, segment functions over their different, stitching together their domains. Then it also allows us to talk about a little more clearly this idea of defining an equivalence relation, so that we say, because this interval maps to the disk and this interval maps to the disk, we can take a point in here and a point in here that map to the same point on the, I said disk, I meant unit circle, that map to the same point on the unit circle and call those equivalent. So they're equivalent mod this popping from one segment to another. And that forms our equivalence relation. Okay, so now we want to build a group, this Blaschke group. So we're going to consider this set fancy C here as the set of all functions U. These are continuous functions that map the unit disk to the unit disk. So they're continuous and they map the unit disk to the unit disk. So as it stands, these form a semigroup. So they're closed and semigroup under composition. So semigroup under composition. And I'll just kind of, we won't prove this, but maybe you could even kind of see if it makes sense to you, or if you can do it. So if we have the convolution of two of these, right, that's going to be a member of the set. So if you take a continuous function, it maps D to D, and then you take another continuous function, maps D to D, then that composition is going to be a continuous function that maps D to D. Associative. So this is closed. Associative. Well, that's an exercise that everybody should do once to show that this composition is associative, but we won't necessarily do that. So this just means that U1, U2, U3 equals U1, U2, U3. There is an identity, which would just be the identity map that maps points, same point to same point. So there's an identity there. But the inverse, no. And one example would be just like the square function, right? That will map the unit disk to the unit disk, but not in an inverse way. Okay, so it is not a group, it's a semigroup. But what we're going to do is we're going to restrict the set now. Okay. So we'll call this set GB, and this is going to be the Blaschke group, to be the set of all functions in here. So the set of all continuous functions, such that when composed with the Blaschke product, we get a Blaschke product. And so there's this theorem, the Cassier-Chalendar Theorem, that says if B is a Blaschke product of order n, then GB is a cyclic group of order n. So that's kind of interesting there. And we could sort of see it putting itself together over here. So we know the Blaschke product will take each of these individual pieces and map them separately to the unit disk. So we're looking for the functions that when we compose that with the function of the continuous functions on the disk, we still get this Blaschke product. So it turns out that sharply restricts the set of functions in here, and it does so in such a way that it does indeed form a cyclic group. And so what happens is we have one function that will map a section I to I plus 1 to the next section. So it's like a push forward function or translation function around this preimage set. So it will map this to this, right? And then the Blaschke product then will take this to the unit disk in the same way. And since we have sort of this idea of this equivalence class, then we get the same result, right? So if we go from here, push it to 1 over, so take a point in there, push that one set over, and then take the Blaschke product, we're the same as if we just started with that point. And so this is true then. Now, we can build then a set of functions. Well, we do 1, and then let's take the composition of 1 with itself. So that would move us 2 units over. So that would take this to, say, here. Okay. And so the generator, we can consider U1 as a generator. I've included U0. This is just the identity map. This, strictly speaking, that's not the generator. That's not a generator. This is the generator here. And we can generate a UK by just composing this k times, and we step our way around. And then UN would be back to the identity. And so we get a set. This should be a B here. We get a set of functions that are just U0, U1 up to UN minus 1. Those are the only functions that will work to satisfy this particular condition. And I think I should have been more clear. This B is the same B as this. So not just a different Blaschke function. Okay, so is this cyclic? Well, just by its very nature, it's cyclic because U2 equals U1 times U1, times being composition. So the group multiplication is composition, and then U3 and all the way around. So indeed, this is a cyclic group. There are n pieces, so cyclic group of order n. Right? And that's called the Blaschke group GB. And so interesting aspect, one of the interesting aspects of the Blaschke group. Now we're going to go on to talk about group theory in a little bit different way with the monodromy group coming up in the next couple of lectures.